In this video, I'm going to introduce the idea of a sampling distribution. And so we're going to imagine that we have a random sample of data from a population, and we want to make inferences about a population parameter, such as the mean. And so one way to do this is to calculate a sample statistic, such as the sample mean, to estimate the population parameter. And then we need to think about the variability in that sample estimate, because after all, we have a random sample from the population that gives rise to a particular value of our sample mean, but we could easily imagine having a slightly different sample with a slightly different sample mean, or a very different sample with a very different sample mean. And so there's variability in this process of random sampling, and so we need to be able to get a handle on the size of that sampling variability, and we do that through the notion of sampling distributions, which I'm going to illustrate with an experiment that we can run in R. So to run that experiment, we're going to set up some data on the length of human genes. So if I go to R now, and I'm going to set my working directory, and then I'm going to install the ggplot2 package and load it, and set the theme so that we have nice pretty looking graphs. And then I'll load the data, and we can have a quick look at the data. We've got 22,385 genes, all with different lengths, and we've got some names and descriptions of those genes as well. But the variable that we're going to look at is size, the lengths of the genes. So to keep the discussion focused, I'm going to exclude any genes that are greater in length than 15,000, and that's just to keep the discussion a little bit easier to follow, because otherwise we have these couple of values that are much bigger than all the others, and it's hard to focus on the important topics. So I'll do that first, and then we'll take a look at the population histogram. So this is a teaching experiment. It doesn't reflect something that we would actually do in real life, because in real life we generally don't have the population to work with. The way that statistics works in the context that we're learning about in this course is that we have a population that we're interested in, but we don't have the means to actually study that population in its entirety. Instead, we're taking a random sample from that population and trying to learn about the population using our sample. But what I'm illustrating here is to imagine that we actually had a population, so that we can see what kind of process is involved when we think about random sampling in real life. So here I've got a picture, a histogram of what our population looks like. So there's a skewed distribution with most of the gene lengths between 0 and 5,000, and then fewer and fewer longer ones. And again, this isn't something we can do in practice usually, because we don't have the population, but in this case we do have the population, so we can actually look at the population mean. So this is the number that we're trying to estimate with our sample, and as I say, normally we don't have this number, but in this case we do, because I'm just illustrating the process. I'm also going to keep track of the population size, and that will allow me to calculate the population variance and the population standard deviation. And the standard deviation in this case for the population is 2,833. Okay, now we get to the part which is going to mimic what we usually do in practice. And we can think of taking a random sample from that population. And so this is the piece of information that we get to see in practice. We usually don't get to see this population. All we get to see is the sample. So I'm going to take a sample from my population, and I'll draw a histogram for the sample. So this is now mimicking what we would do in practice. We would look at the data, which in this case means looking at a histogram. And you can see that the histogram has some features in common with the histogram for the population, but it's also very different. There's a lot more noise in here because it's a lot more wiggly. If we go back to the population one, it was kind of a nice smooth curve, whereas this one is a lot more jagged, but it does still have that flavor of being skewed. There's a lot more values down here between 0 and 5,000 and fewer larger numbers. When you do this for yourself, don't worry about this warning message down here. That simply means that in our sample we happen to get one row that exceeded 15,000. And so in this case, because I want my histogram to match up with my population one, I'm truncating it at 15,000, and so this is simply telling me that in your sample you've got one value bigger than 15,000. Okay, so we have our sample now. We've taken a look at it in a histogram, and now I can calculate some sample statistics. So for example, the mean and the standard deviation. Okay, so at this point we could say, here's my sample mean, 4,181.01. I'm going to use that to estimate my population mean. Okay, and then we might ask ourselves, how confident am I that this is close to my population mean? Well, normally that's kind of a difficult question to get your head around, but in this case we can actually look and see how close it is because we happen to know our population mean. It was 3,511.457. Okay, so we're a little high. It's not totally wrong, but it's also not that close. So I don't know. It's a little tricky to answer that question of how accurate is this at the moment. We don't quite have enough information. Let's do this over again and see if we can get a better handle on that uncertainty in that question. So we'll take another sample. Okay, it's going to be different from the first one we took. You can see that if I draw the histogram, looks a little different. And then also if I calculate the mean and the standard deviation again. This time I got 3,568.22. That seems a little better. 3,511.457, that's what we're going for. This is actually very close. But let's just think for a second. In practice, we only get to see one sample. We don't get to do this over and over again until we get close. We only get to do this once, and we don't know how close we are because we don't get to see this number. So we need to have a way of assessing the variability in these sample means when we just have a single sample. Let's do this a couple more times just so you can get a sense of the variability here. So here's another sample. Here's its histogram. This time I'm pretty low, 2,861. Let's do it again. There's the histogram, there's the sample mean. A little closer than the last one, but it's still a little low. And let's just do this one more time. There's the histogram, that's the sample mean. Okay, so you should be able to get a sense of the sampling variation in the sample means. Each time we take a sample, we get a different sample mean. And so what I'd like to be able to do at this point is say, okay, I've got one sample. I can calculate this. Let's suppose this is my sample, this sample that I just took. I've got this number, 3,324.2. How confident can I be that this is a good estimate, relatively close to my unknown population mean? Remember, normally that population mean is something we don't know. So it turns out that there's some statistical theory that was done many years ago where someone figured out the answer to that question. And what they said was, well, if I look at the standard deviation in my sample, and then I take that standard deviation and divide it by the square root of the sample size. So the sample size, in this case, it's 100. So then I calculate that standard deviation divided by the square root of 100, which is 10. So I'm going to get 281.107 for my what's known as a standard error. Okay, so the standard error of the mean is the sample standard deviation divided by the square root of the sample size. And what this is an estimate of the standard deviation of sample means taken from repeated samples from the population. Okay, so what am I talking about here? All these sample means that we calculated. So we got this one, 4,181, then we got this one, 3,568, then 2,862, then 3,404, then 3,324. If I had a whole bunch of those numbers, and I was to take the standard deviation of those numbers, it would be estimated by 281.107. This standard error of the mean is an estimate of the standard deviation of sample means from repeated samples from this population. Okay, it's known as the standard error of the mean. Okay, and it gives me a sense of the accuracy of this number with respect to it estimating the population mean. Okay, so this is one part of understanding how to quantify the uncertainty that's inherent in this estimate of the population parameter. In the next video, I'm going to show you how to combine this sample mean with this standard error and come up with an interval that will give us a certain amount of confidence that the population mean is in the interval. So that's what we'll do in the next video.